Morning, welcome back to our Economics of Regulation course. Before I start with the stream, I just would like to ask you to join me in the Webex chat to give me any feedback we might have. Okay, so we just start with the stream right now. Good morning, welcome back to our Economics of Regulation course. Last week, we finally started with our, modern theory of incentive regulation. Our basic setup was that of a principal-agent model, where the regulator is the principal, the regulated firm is the agent, and the regulator has to deal with the problem that the agent is better informed about some characteristics. This is our basic asymmetric information problem. We started with this discussion, and I just tried to jump back to the respective slide where we ended. I think this is, in a sense, what I presented at the very end of the last lecture. I want to show you now the basic framework or the unified framework we try or we employ in order to solve the adverse selection problem we are dealing with in that chapter. First of all, we assume that the firm has some private information and that this information is binary. So we looked into the Baron-Meyerson model where the regulator was not informed about the marginal cost of the firm. These marginal cost of the firm might have been either high or low. Fixed costs were common knowledge, and demand was also knowledge. And then we looked into the different kinds we could have or ways we might have asymmetric information problems. Apart from the Baron-Meyerson model with the marginal cost being unknown, we looked into the Lewis-Seppington setup, I think it was in '89, where both marginal and fixed costs were unknown, but where we had a specific relationship between marginal and fixed costs. So if we had high fixed costs, we knew that we have low marginal cost and vice versa. And then we further looked or briefly introduced the La-Fortiero model, where the marginal costs were observable, but it was not clear what the relation between marginal cost and the required fixed investment is. So we could reduce marginal cost, but it was not clear how costly that is. I will get back to that later on. And finally, we had a Lewis-Seppington model, I think it was '88, where demand is unknown, that the firm might face high or low demand, and the regulator does not know. And as always, we assume just some certain probability phi with which the demand is the firm is a low-cost firm or demand is low, and so on. And we denote some notation here, the firm's profit in state I as pi I, and this is a function of typically the price it charges. And now the important point we are doing is, what we are doing here is mechanism design. We want to design, we want to derive a mechanism so that the regulator maximizes welfare, and she does so by specifying a certain contract. And the contract specifies, first of all, the price of the regulated firm charges, and second, the transfer. Actually, we will see later on that the firm self-selects from a menu of contracts. Finally, what we also discussed was the firm's rent. Now, of course, as we allow for a transfer, we no longer have to observe something like a break-even constraint, but we just can pay rents, and actually will pay rents, the so-called information rent, to the better informed firm. And what we denote here as RI is just the rent of the firm, and made up of the profit plus the transfer. And what turned out as a very important variable in our model is the so-called profit difference, the difference between the profit, the high type, the high cost type, for instance, has given a certain price minus the profit the low type has. Actually, it turns out, and I showed you that briefly last week or 2 weeks ago by depicting it graphically, this is just the incentive to cheat, okay? Because that's what the firm gets if it claims to be a high type, what the low type gets. Okay, that's what we can much better show here in this diagram. Suppose here this difference in profits here. Suppose the price the regulator sets for a high type is CH equal to the marginal cost. So we are in a Baron-Meyerson setup here. The marginal cost of the low type are CL, and if the firm the low type actually claims to be a high type, this red rectangle would be just the profit gain it gets from this cheating. And this is actually this difference in profit. And here you see in Baron-Meyerson, of course, that's negative because we subtract the profit of the low type from the high type, and the low type is a low cost type. So it's CL minus CH times the output here. So this is this triangle, actually the minus of it. And an important property which will be very relevant in what we do next is that this profit difference is increasing in P. What does this mean? Now, as this is typically a negative expression or a negative term, increasing in P means that the difference becomes smaller in absolute terms. Okay? And that's what we immediately see here. If the regulator prescribes the price PH, which is higher than CH, what we immediately know, the regulator knows, of course, that these blue rectangle will be profit of a high type. It will actually just reduce the transfer, which would be equal to F in the standard setup with price equal marginal cost, which will be equal to the fixed cost in that setup. It will reduce this transfer by this profit. And so the profit difference is only the green area now. Okay, and this is again the incentive to misrepresent, and this incentive to misrepresent or to cheat decreases with a higher price. And what we will show is that in such a setup, typically it must hold in equilibrium. If you have a separating equilibrium, I will explain in a few minutes what that is, that the price of the high type is greater than the price of the low type. Okay, I think that was about what we discussed last week, and now we have to solve, okay, our optimization problem. How should the regulator set its contract, or which contracts should the regulator offer? And of course, we need a standard kind of objective function. We know we have to start with the consumer surplus, V, which is a function of the price the firm charges. Of course, we have to subtract the transfer because that's taxpayers' money. If we would have a distorted tax system, we would get some capital lambda here, but I don't go into detail here. We did that in chapter 8. And then the welfare in state I, either high state or low state, is simply this net consumer surplus in this state plus alpha times the revenue in this state. And of course, the state might be either high or low. And here, of course, as we introduced, the rent of the firm does not enter as in standard partial equilibrium analysis when we consider total surplus, where the rent of the firm gets just the weight of 1, and we just sum up consumer surplus plus profit, or producer surplus. Here we assign only a weight alpha, which is something between 0 and 1. Okay, very often it will be just 0. We might rearrange that, and I just want to get rid of my lines here. We might simply rearrange that by adding pi p here and subtracting pi p here. Okay, just expanding, and what you see here, if you can read that, this expression is nothing else than our total welfare. Okay, and minus pi p minus ti is nothing else than r, or minus r actually. So that's why we get this minus 1 here. So we can easily reformulate that. And is it better? Okay, that was the question what I'm asking here. Actually, it's nice in a way that we know here what the regulator maximizes is just total surplus, but has to take into account that rent of the firm is socially costly. Okay, this is this minus 1 minus alpha times r, and it would not be costly, and that's a standard case in standard partial equilibrium analysis if alpha were equal to 1. Okay, then expected welfare. Of course, we have a certain probability phi that the state is low, and a certain probability 1 minus phi that the state is high. So the expected welfare is just the expected value of this here, phi WL plus 1 minus phi WH. And what I also hopefully introduced before is that we have to take into account 2 so-called participation constraints. In a sense, these are our non-negativity constraints. The rent of the firm has to be non-negative in each state, irrespective of whether it's high or low. And our first, or our starting point, is always the full information outcome. The full information outcome is that we know, our regulator knows which type the firm is. Of course, if the firm is if the regulator knows the firm, actually we wouldn't pay a rent because we know the rent is costly. Okay, and therefore we simply maximize. We know what this type is. We simply maximize total surplus, and maximizing total surplus would just mean that we get price equal marginal cost. But we will get back to that, because if we maximize in a general case, we see as a boundary or as a limit case the case with full information. Okay, unified framework here. Asymmetric information, that means we have to take into account also incentive compatibility constraint, the ICCs. What does that mean? I think I also briefly introduced that, in particular in terms of our diagrams. Our low-cost firm must not have an incentive to pretend she's high cost. And vice versa, that's what will be in the next. The high-cost firm must not have an incentive to pretend she's low-cost. And here I just show you what that means in more formal terms. Okay, in terms of our rectangle, if we want the firm to tell the truth, we would have to pay a transfer which is equal to the rectangle in order to make it truth-telling. Now what we are doing here is the rent the low type gets in the case in which it accepts the contract which is tailored for it. Okay, so the regulator offers two contracts, a contract PLTL and a contract PHTH. The firm will only say it's a low type and therefore accept the contract PLTL if the rent from truth-telling is at least as high as the rent from lying, from cheating. Okay. Now, what the rent from truth-telling is clear. It's just the rent if you set the price PL and you receive the transfer TL. What is the rent from cheating? If you cheat, the price you get is then the price of the high type, and you get a transfer of the high type. Again, you can rearrange that by just adding here. I have to get rid of my lines here. By just adding and subtracting here minus pi h p h plus pi h of ph was supposed to be a plus. Then this thing here, this expression with these two profits is nothing else than minus our profit difference, and pi h plus th is nothing else than our rent of the high type. So that's how we can rearrange that, and so that you don't wonder why we get the RH here. We just write it differently. And so the important point is here we get this, as I told you already, this difference in profits, and that's actually the incentive to cheat. Okay? And yeah, this will become clearer further on. You will see RH will often be 0, and therefore it's just our rectangle. And that's what we will go to, I think, in one of the next slides. Yeah, the respective incentive compatibility cost of the incentive compatibility cost rate of the high cost firm looks analogously, and I don't want to derive it in detail here. You just see it's completely analogous. Okay, RH must be greater than RL plus this delta pi PL, and it's just the same thing here. And the important point is that both in an equilibrium, both incentive compatibility constraints must be satisfied. What does this mean? We know here the first stage was that RL, that's the incentive compatibility constraint of the low type, that RL must be greater or equal than RH minus delta pi pH. And at the same time, we know that this RH here must, from this condition, of course, or we can just substitute that here if you observe it, and so we can get this here, RL. Okay? RL plus delta pi PL minus delta pi pH. That's what we get here. And if from this inequality, it's obvious that if we just subtract RL, so we would get 0 here and 0 here with respect to the RL. We just can put the minus delta pi with plus delta pi pH on the other side, and what we get is delta pi pH is greater or equal from this inequality sign here than delta pi PL. Okay, that's what we must have. Yeah. So what we will do, and now we already consider this incentive compatibility constraints. We saw what we have to satisfy it, or what must be satisfied. We will see later on now delta pi pH will be greater if pH is greater than PL. Okay, that follows from this property of this profit difference, that it's increasing in the price. Okay, now what we are doing here is we look into a constraint which guarantees that the firms tell the truth. Is it worthwhile to do that? Actually, that's what the very famous revelation principle shows. If a regulator or a principal offers a contract, it can constrain the set of contracts to the contracts which induce truth-telling. It's always better to induce truth-telling or any contract which does anything, okay, but not imply truth-telling. You always find an equivalent which implies truth-telling, which gives you the same trade-off. Okay, Armstrong, Sepping put that in a footnote 12 as follows: the revelation principles ensures that the regulator can do no better than to pursue such a policy. So we always want to make truth-telling, and I already told you or showed you that's actually a good idea to make the firm truth-telling. I will get back to that in a minute as well. Okay, I just have to look up whether, I think I already explained everything to you. As always, if there are any questions, just drop me a note in the chat, okay? Yeah, I think here I just rearranged it slightly. You see, you can also put this profit difference differently. I don't go into detail here because I only will get back to that in the next slide. I just employ here the definitions and just rearrange it, but that will be more important on the next slide. Okay. Now, what we are doing now is just look into what the full information outcome would require, what it actually mean, and under what circumstances is that satisfied, or under what circumstances in which world can we get the full information outcome, even if we face asymmetric information. The full information outcome obviously is clear. It will be price equal marginal cost and no rent for the firm. Remember that rents are costly, okay? Then the question is, under what circumstance is the full information outcome feasible? And of course, it's feasible if, here we already would satisfy the participation constraint, and it's feasible if the incentive compatibility constraints hold. And these two incentive compatibility constraints were just as written here: RL is greater or equal than RH minus delta pi PH, and RH is greater or equal RL plus delta pi PL. And that simply means, given that we assume here, or that we require here that RL, RH is 0, we immediately get a condition on the profit differences, namely that the profit difference for PH must be positive and the profit difference at the price PL must be negative. Okay, what does that tell us? It's yeah, that's what I already told you. Delta pi PH must be greater than 0 and delta pi PL must be smaller than 0. Or put it differently here, just using the definitions here, the profit difference here, yeah, I think this is just the same. The point here is information asymmetry is not socially costly in this case, and the profit functions must cross, yeah, because here in the starting point, pi h must be greater than PL at the price PH, and pi h must be smaller than pi L with a low price. And that's what actually I also do here in more detail here, but it's very easy here because you already see it immediately. I just derived it in one more step, just go through it. It's already obvious from here because you only get a positive sign for this difference if pi h is greater than pi L in one case and pi h smaller than pi L in the other case with the low cost. In a minute or in next slide, we will get an example so that it's hopefully much clearer. The important point is that this is never possible with Baer-Meyers. And why is it not possible? With Baer-Meyers and the low marginal cost, of course, has always a higher profit than, given the fixed cost, than the high marginal cost. Okay, it never holds in Baer-Meyers, and it also holds not in Lafont-Tirol, because the firm which has a lower investment cost or a lower effort for a given marginal cost realization will always have a higher profit. Okay, it's not possible with Baer-Meyers and it's not possible with Lafont-Tirol, but it's possible with the Louis-VIII models, and I think that's what we turn to next. Okay, the Louis-VIII model, and hopefully that become clear right now what all these conditions mean and under what circumstance we really can implement the full information outcome in a world where we have asymmetric information. Okay, the regulator does not know whether the firm has marginal cost CL and fixed cost FL, or marginal cost CH and fixed cost FH. Okay, now what is clear? So that's our setup. Remember, both marginal cost and fixed cost are unknown, but there is a relation between marginal and fixed cost. So if fixed costs are high, marginal cost will be low, and the other way around. Now, of course, the profit of each type is, of course, here just a function of the price, and it determines the quantity, and yeah, as always, operating profit minus fixed cost. Then our profit difference here. Remember, we have the profit of the high type minus the profit of the low type, and what we see here, profit of the high type again here. What drops out is just a P, and we get a minus CH here. Oh, I just added here pi H minus pi L. Okay, of course, we should have here the P and here the P as well in brackets. That's what we get. And now what we get here, minus CH minus CL. That's in a sense like in Baer-Meyers model, but here we have a second term here, which is just from the fixed cost. And why is it so? Now, here the point is we get a difference in fixed cost. Here we subtract the fixed cost of the load type, and we get this fixed cost difference as well. Okay, so the point is here, high type, the high marginal cost type, has lower operating profit, but at the same time might have nevertheless a higher profit as it has lower fixed cost. Okay, that's what we get here. And full information prices and transfers are, of course, price equal marginal cost, and transfer equal fixed cost. And of course, what we have to make sure now is, if we use, or if the regulator offers these contracts, will we get the full information outcome? That is, will the load type truthfully reveal that it's a load type? Will the high type truthfully reveal that it's a high type? And therefore, we get this first best or full information outcome. What we already had here were the two incentive compatibility constraints. Of course, RL, RH should be 0, and then we put that on the other side, the delta pi pH, and this delta pi pH is nothing else than what we've written up here, and this is supposed to be greater than 0. At the same time, the profit difference at the load price must be smaller than 0. That's from a second incentive compatibility constraint, from the compatibility constraint of the high type, and that's what we get here. Okay, awful expressions, I admit. Okay, but what does it mean? Now, yeah, that's what I try to show you in the next slide, because, or in the next line here, because now we have two conditions on actually very similar expressions. Okay, and these two conditions must hold at the same time. So we could put the FL, FH here on both sides here, but I just put FL minus FH here in the center, the minus CH minus CL on the other side here. That's what's written here, and here the CH minus CL of QPL. PL will of course be CL. So on the other side, so this just rearrange these two conditions and put them together, because we know this line here, okay, must be greater than 0. This line here must be smaller than 0. So here we get a 0. Put the FL minus FH really on the other side, okay, by accordingly subtracting. So here from this condition, for instance, we get that FL, I think I just do it like this here, because I even animated here or highlighted it. So which condition is this here? This is actually here our, and I have to erase all my lines here. This condition is actually the second condition here, okay? And you see immediately putting the CH minus CL times Q of CL then, because of course we want to implement the first best. Putting that on the other side, we get CH minus CL times QCL is greater or equal than FL minus FH. Okay, that's from this condition. And from the other condition here, we get that FL minus FH from the incentive compatibility constraint of the load type, we get that FL minus FH is greater than CH minus CL times Q of pH, but pH, if we implement first best, is equal to CH. So that's what is here. Okay? Okay, and these two conditions must hold, and what do they mean? QCL would be the output of the load type, which is prescribed for the load type. If the high type claims to be a load type, it has to cover a loss in terms of, again, a rectangle, okay, and in terms of operating profits. And this loss, and now I'm back again here, the point is they are very similar, these two conditions. This loss must be greater than what you gain in terms now of the higher transfer. You claim to be a low type, so you receive the high transfer, even though you have only the small cost. And here is what you see. Your loss is greater than your gain in terms of the higher fixed cost transfer. And on the other side here, and that's where I'm here, I should have looked into my notes probably. Here is the point. Here is QCH, that's the quantity prescribed for the high type. If you're a low type and claiming to be a high type, that will be output. This will then be your operating profit, your gain from cheating, but at the same time, and now this applies what I already told you in the very beginning, it's now that you have the high fixed cost, but you only receive the transfer on the low cost. This will be very straightforward. I think we have a nice problem in assignments where it's really straightforward, where you just calculate this range for the fixed cost so that this applies. Because it is so... Okay, I think, I don't know whether you have the impression that I did a good job in explaining that. I don't have the impression. So that's why I just simply changed the slide a little bit, which you see here. Okay, so this is now live in a sense. what you see here, I want the two ICCs, the two incentive compatibility constraints, to be satisfied. The first one is that of the L type. Our incentive compatibility constraint, as I already explained, is just RL. The gain from telling the truth, in a sense, is better than if you claim to be a high type. Now, if we are in a full information outcome, we know that RL and RH will be 0. So we want to check whether we get here RL equal to 0. That would be here. And of course, if you claim to be a high type, you would get the contract PL equal, if you claim to be if you correctly tell the truth that you're a low type, you would get this contract TL FL, or TL is equal FL and PL is equal CL. And of course, that gives you a profit of 0. And if you claim to be a high type, here this RH, then it's clear you get the price equal CH and you get a transfer equal FH. Now, this is then your price, this PH, or this CH minus CL. So this would be your operating profit. Then that's what I always tell you as the rectangle. Hopefully this doesn't confuse you too much. And on the other hand, you have to bear the fixed cost. Your fixed costs are these FL, but you get then this FH as a transfer because you claim to be TH. Okay, that's actually rather straightforward, hopefully. And this is just our condition we just discussed. So this would be the incentive compatibility constraint of the L type, and this right-hand side expression here is nothing else than this minus delta pi pH. Okay, and the same thing in the next line. So that's one part of this condition you saw, and the other part is what you just get if you look into the incentive compatibility constraint of the high type. And then of course this RH, you get if you truthfully tell that you are a high type, you get of course PH is equal to CH and TH is equal to FH. So you get your marginal cost as a price and your fixed cost as a transfer, and this is then of course 0. And RL, of course, or what you really have then is that if you claim to be a L type, you get the price PL, which is equal to CL in this full information outcome. So this here is of course your price. If you claim to be a low type, of course these are your marginal cost. Of course that gives you this operating loss if you claim to be a low type, if you have high cost. But at the same time, you only have, this is this minus, this FH as your own fixed cost, but you get this FL here as transfer. Okay? So how can it be possible that the incentive compatibility constraint is not satisfied here? Now, even though you make a operating loss, it can be that the high transfer you receive, because the FL, the fixed cost of the low type, are so high, that the high transfer you receive more than overcompensates for your operating loss. And now, what you actually saw then in this condition here is, here are just the two conditions I just gave you. I just rearranged the one. We can just rearrange the two conditions here, put them together. Here you see here on the left-hand side, this is greater or equal than 0. You can actually, I put this on this here to the right-hand side, as you see. So you see FL minus FH is greater than this CH PH here, okay? And on the other side, put this minus CH CL PL here on this side. So this is greater, and therefore you get something in between. And what should be clear as this, and that's what I just explained to you, and I of course could here rearrange it. This CL, of course, this quantity Q at this low price is higher as this quantity Q at this high price. So we know this thing here is larger than this thing. So we always get, or there exists a range of this difference in fixed cost so that both conditions are satisfied. Hopefully it was clearer in 2 minutes about we will make a break, and so we can get back to that, and you can tell me whether this explanation was better than the one from the last year. No, it's not so complicated, but it's just tedious, and you have to really take care of what you are doing. I just illustrate here in terms of this diagram. Okay, what happens here? I think here it should be closer. I use certain parameters, for instance, that CH is equal to 40, so CH would be equal to 40, CL would be equal to 20, and yeah. So here you see, if I tell you it's CL, then I should also write CL and not CH. Okay, hopefully this has been clear to you. Have some value for FL, it would be 1900, FH would be 500, and the quantity or the demand function is just 100 minus P. What you see here is this crossing property of the profit function. What does this mean? Now, if you actually are if you're a low type and if you claim to be a high type, the point is this is your profit line. And if you claim to be a high type and you're a low type, actually your marginal cost will be 20. Okay, your marginal cost will be 20. So the price will be 40. So you make on each unit sold, you make a profit of 20. Okay, at a price of 40 and demand function 100 minus P, you will sell 60 units. So you get an operating profit of 2,400. You get a revenue of, I better write it down here, PH 40, so CH or PH minus CL times Q of PH 60 would be just 1,200, okay? Would be just 1,200, I guess, and you get a transfer TH of 500, okay? But your fixed costs FL or 1900. So you get 1900. So the point is what you see here, the operating gain you have is not sufficient to cover your high fixed cost, and that's what you see here. You make a loss because you're operating, you have here 700 and you get only the 500 transfer. You get 700 in terms of operating profit here from your gain from cheating. And what you also see here, this delta pi p is positive here. Okay, the profit of the high type is higher for the high price than for the low type, and for the low price it's just the opposite. Okay, yeah, again, hopefully it only or it really only becomes clear once you calculate the example, the problem in the problem set. Okay, I think I make a very short break here and just look whether there are any questions. Okay, same here. Just one final point. Hopefully it was clear. You see this profits are always in the negative territory at the cost, but that's rather clear because you have price equal marginal cost, and then you have also fixed cost. And if you look at the blue line, perhaps I'd show it here to you once again. If you look at this blue line as this pi h at the price equal marginal cost for the high type, price equal marginal cost, operating profit is 0. And here you see exactly the profit would then be this minus 500, which is equal to the fixed cost as assumed, as you see in the notes. And of course, this would have to be covered. By means of a transfer. Okay, so short break here, and I ask for questions in Webex. Okay, so we just move on. For those of you who didn't join me already in Webex, just join me to ask questions. Okay. Okay, we move on, and as always, of course, this is complicated stuff, but it will be much easier, much straightforward once you. I think I could just show you that once you do this example here in, I think it's, where is it? that would be our Lewis Sappington example here, where you have to explicitly calculate this FL here so that our incentive compatibility constraints are satisfied. Okay? Okay, so then we move on. Probably this is too hard stuff in order to have already now a question. It really will become clearer once we look into the problem set and apply what we are doing here. And you really will see, okay, even though we have this asymmetric information, even though the regulator does not know is this a high or a low type, nevertheless, the regulator can implement the first best. And that's what we also see in the next example, where demand is uncertain, or demand is unknown. It's unobserved by the regulator. Of course, it's known to the firm. And again, we assume that it's high or low type, high or low demand. And the important point is that we assume a convex cost function. That means we have increasing marginal cost. Demand is either high or low, and the high demand has, for the same price, a higher quantity than the low demand. Inverse demand is given. We have some probability of low demand, which is phi. Remember, we always have the phi as denoting the L type. And the full information outcome would just mean price equal marginal cost, as always, and a transfer to cover or to make sure that the profits are non-negative, to cover the fixed cost. What we have to take into account here is that the firm will make some operating profit. That's what we immediately see in the diagram, because here you have marginal cost, price and quantity, high demand and low demand. Now, what is clear, we get always price equal marginal cost. So the high type would have this price prescribed, the low type would have this price prescribed. Now, given we offer these contracts, that is PL equal to marginal cost of the low type and PH equal to the marginal cost of the high type, and pay a transfer equal to the minus the profit. So what does this mean here? Of course, our starting point now is a high type, a contract for the high type. How does that look like, the contract for the high type? Now, what is clear, the high type gets this P. I think I didn't even denote this, get this PH'd. Now the high type, you know, the revenue is just here, this rectangle, okay? The whole rectangle, and the area below the marginal cost curve would be just the variable cost. This would be this. So revenue minus variable cost, the yellow area, is just operating profit. And so this firm, the high type, would receive a transfer equal to the fixed cost minus this yellow area. Now, what would happen, and I have to erase it again, what would happen if a low type would claim to be a high type? Now, the low type would then have would only sell this quantity, okay? This would be Q of the low type given pH, okay? That would be the quantity. And with this quantity, of course, operating profits would only be the yellow area, but it has to pay, remember, a negative transfer actually is taxed by the previous yellow area, which is now the yellow plus the blue area. And it has really a loss, and I have to erase again here, a loss in terms of the blue area if it claims to be the high type. Okay? So the point is here, our low type does not have an incentive to claim to be a high type because it would make a loss, given the regulator offers the contracts the full information of the full information outcome, the full information contracts. Okay, hopefully this was clear. It hopefully becomes even clearer once we look now into how the world looks like for a high type who claims to be a low type. First of all, what is the situation for a low type? Now, of course, for the low type, the regulator will prescribe a price PL equal to where price is equal marginal cost. And similar, this red area now is the transfer or the tax the firm has to pay. It receives now a transfer equal to the fixed cost minus these operating profits it makes. Now, how does the world look like if a high type claims to be of the low type? Of course, our price stays the same. And now the demand or the quantity the high type gets is the Q of the high type given the price of the low type is just this here. You see again the area below the marginal cost curve is the variable cost. Again, I could draw here just our revenue, okay? And you see clearly that due to the situation here where it's actually the price is below marginal cost, this would be the purple area would be just a loss to the firm. Okay, it would receive here this red area. Excuse me, it would have to pay this red area as this is operating profit, and then it would in addition have this loss. Okay, this is now a loss because these are costs. Marginal costs are way above the price, and our revenue is just this rectangle here. Our costs are the area below this, and I further have to pay the red area, not rectangle, but triangle. And what I have here is a huge loss from claiming to be L if I'm a low type, if I'm really a high type. So what you see here is we are somehow in a very strange world, in a miraculous world here, a wonderful world. We only offer the first best contracts, and even though we do not know what the demand really is, the firm has no chance then really to truthfully reveal its type. Okay, yeah, that's what we get here as a result. Finally, one short point I perhaps should mention here, that we assume that a firm must serve all customers willing to buy at the current price. Okay, that's an important point here, but that should be clear. Yeah, unfortunately. Okay, so here, of course, a key assumption is that we couldn't observe the demand. Of course, that's always a question: can the regulator observe the demand? How many people buy what? Think just of our Corona or COVID-19 test centers. Does the Federal Ministry of Health know how many tests really have been applied? Okay, so that's always or might be a complicated problem for a regulator to monitor really the quantities. Okay, I don't know how well it fits, but that came to my mind. It's not always this easy, and so for instance assume that we are in a Bayer-Meyerson world, and assume that in a Bayer-Meyerson world you just assume that we are in a Bayer-Meyerson world, and assume that in a Bayer-Meyerson world you just offer the full information outcome, the full information contract, that is price equal marginal cost and transfer equal fixed cost. Then in a Bayer-Meyerson world, you simply, the low type would simply have the incentive to cheat. Okay, I just think again show you that in terms of 1 hour of our diagrams here. Here is our diagrams. If in a Bayer-Meyerson world, I just jump back here. In a Bayer-Meyerson world, the regulator offers the first best contract, that is PH equals CH and T equal the common fixed cost F, and the same for the low type, PL equals CL. The low type would have a profit of 0 if it tells the truth, and it would have a profit equal to the a rectangle here if it cheats and claims to be the low type. The high type, of course. Now, what we are doing in this situation? Now, if we offer these two contracts, we would get these two full information contracts. We would get a so-called pooling equilibrium. All types would pick the same strategy in all states. Okay, if we, and that's what we will construct in a minute. If we offer two incentive compatible contracts, and the low type will choose a different contract, then the high type we will get what is called a separating equilibrium, because not all types use the same strategy. So this definition is from Eric Rasmussen's game theory book, and it should become clear. So we will get pooling strategy, pooling equilibrium later. For the moment, we are looking into separating equilibrium, and yeah, here I further define what pooling is. All types receive the same transfer and charge the same price. Actually, all types will really then choose the same transfer and charge the same price. And with the separating equilibrium, that's what I already told you, different types receive different transfers and charge different prices. Now, the point is already, of course, we saw that we have to pay some rent. And the point is now we are looking into what the optimal solution looks like. And what we will see is that it's very important that the rent in state L is inversely related to the price PH. That's what I already also showed you with means of these rectangles in a previous diagram. You will see that the regulator has an incentive to distort the pricing decision of the high type compared to the full information outcome in order to reduce the rent of the low type. And that's what we are going to derive in, say, the next 2 or 3 minutes or 2 or 3 slides. Again, or we start with the point that the profit difference is always negative for all P. That's just what holds both in Baer-Meyerson and in Lafont-Tirol. What does this mean? The high type has higher marginal cost or higher fixed cost, and so the profit of the high type is lower than the profit of the low type for all prices. And therefore, the only relevant participation constraint is that of the high type, because the high type can never claim to be a low type because it has higher cost, and therefore the only thing we have to guarantee in order for the high type to really produce is that its rent is non-negative. How does the IC constraint look like? Yeah, that's actually what we had. I think if it works here, I can jump back. That's what we derived here. Okay, that's what we derived here. These are just actually is. Here, this condition, the only point is that we here set the RL equal to 0. If we don't set it equal to 0, but set RH equal to 0, we get RL is greater than minus delta pi P, and it's also greater than, and it's smaller than minus, it's greater than minus delta pi PH, and smaller than minus delta pi PL. And what we did here is we looked into the other we just turned it around. Oh, not even. We use a minus here. Okay, what is always a problem for me, you have to be so exact because it's delta pi PL then delta pi PH. Okay, the point is, or what the important point is here, this is really the incentive compatibility constraint of the low type. I just call this ICCL here, okay? The rent of the low type has to be greater than the profit difference if it charges, or if it claims to be a high type, okay? That's what we had here. Always think, if it's too complicated, always think in terms of the rectangles. The left inequality doesn't matter because that's actually the incentive constraint of the high type, that the high type does not pretend to be a low type, but that doesn't matter anyway because the high type can never, that's never binding, the high type can never do that. And what we also know is that we always want to have, in terms of our rents, a strict equality because we don't want to pay more rent than absolutely necessary because rents are socially costly. Okay, so hopefully this became clear. We will have many nice problems on this setup, and it will become clearer. So I don't expect that you immediately understand this very complicated stuff now when you first listen to it. The problem, or the nice thing about YouTube is that you just can go back later on and listen to it again. Okay. Now we want to derive finally the optimum in this separating equilibrium. So what we want to derive is really two contracts or a menu of contracts, or actually it's two menus, two prices and two transfers. A price PL and a transfer TL tailored at the low type, and a price PH and a transfer TH tailored to the high type. Okay. Now, in order to do that, in order to derive that, we have to maximize welfare. And what is welfare? And that's actually what we just derived up there. And again, WIP small w is just total unweighted surplus. And now you might think why we did all this stuff here. Actually, we have a complicated optimization problem, and we have to determine here, and we have to maximize welfare, and we have to choose PL, PH, TL, and TH. Okay, the point is here, and we have to observe the participation constraint of the high type and the incentive compatibility constraint of the low type. Now we already know the participation constraint of the high type. PCH simply says that RH will be equal to 0, and this determines already from that we get immediately TH once we have PH, the price, okay, because we know then what the loss will be or the profit will be. And at the same time we have ICCL, the incentive compatibility constraint of the high type, and we know immediately what this is, namely it's minus delta pi PH. That's what we, oh, you wouldn't be able to recognize it, but I told you, and actually it's what is written here anyway. Okay, but the point is here now we have a very nice optimization problem where we now just set our welfare function and got rid of anything related to TL and TF. We get TF from the participation constraint of the high type, and we get TL from the incentive compatibility constraint. Gives us TL, okay, and that's what we have here, okay. That's this delta pi pH, and here we got here we have a plus because we know even though it's here. Up here, it's a minus, okay, can you see that? Up here, it's a minus with Ri, but as I previously wrote, and I erased again, this delta pi, this profit difference is negative, okay? Yeah, now what we have here is our welfare. Our welfare is just welfare in the low state. We have to multiply it by phi, the probability in the low state. It's total surplus in the low state plus this 1 minus alpha. The rent is actually minus 1 minus alpha the rent, and the rent is equal to minus delta pi pH. Okay, and this is again our rectangle. Okay, and here in the high state it's plus 1 minus phi WH pH. And now we maximize that very simple profit maximization problem with respect to PL and pH. Now PL only shows up here actually in the total surplus, okay, WLPL, and I don't jump back, but we already know that if we maximize total surplus, that's what we are doing here. We get as a result, and here I would have the link to some slide on chapter 8, but I just don't jump back because you know we always get P is equal to C, price is equal to marginal cost, if we just want to maximize total surplus. And that's our very important result, and it's a very general result. This result you always also see in related problems in optimal taxation. There is no distortion at the top, it's called there. Here there is no distortion for the efficient type in a sense, okay? No distortion in state L. And now pH, and here I put it slightly different. Actually, Armstrong suggested this here, and Armstrong-Sappington. What you see here in our welfare function, pH adds here in 1 minus phi, and it enters here as well in the problem here in the L state here, because, and that's why does that? Because you know by changing pH or by changing distorting pH, you can change the rent of the firm, okay, of the low type. And now here, what we did here, we just maximized or divided this by 1 minus phi. Okay, that's what shows up here. Why is that so, or why is it so interesting? Because you see, pH now maximizes total surplus minus something. Okay, and here this minus something is the rent. Okay, that's what we have. Okay, and now we just take the first derivative with respect to pH and get some optimality condition. If we take the derivative of the total surplus with respect to P, we get this condition here, which actually up here, as we didn't have this second term, led to the result that price equal marginal cost. But here you see you have something where now this part, the derivative of the profit difference with the price enters. Okay, and this derivative, that was a very important assumption, is positive. Okay, if we increase the price, the rent decreases. Okay, in absolute terms. Okay, and what we immediately see, put that on the other side, you get something negative, divide by Q prime, which is also negative because it's the slope of the demand curve, you get something positive, and you see P minus C is something which is positive. And therefore, price is distorted upwards, price is higher than marginal cost. At least this holds as long as this expression here, the delta pi dp has a positive sign. And this does, for instance, not hold in a Lafort-Tirol model, but we will get back to that later. And what we also see, of course, if alpha would be 1, the rent wouldn't matter, so the distribution of the rent, and therefore we wouldn't get a distortion. Similarly, if phi approaches 0, we would also get price equal marginal cost, pH equals CH. Why is that so? Now, if phi is very close to 0, that means that there's a very, very low chance that the type is really low type. Therefore, we don't want to distort in 99% of all cases this high type, given that we have a 1% chance that we have a low type. But here now we already have our result, okay? And what we are doing next is just applying Baer-Meyerson. And Baer-Meyerson, hopefully, yes, I did. Baer-Meyerson was just a situation where both firms had the same fixed cost F, but firm type L had a low fixed cost. Okay, hopefully that was clear so far. I don't make a break here because I think the next part should make that or should illustrate that better, because here you will see now we apply this rather general or abstract way to proceed, and hopefully then it's rather clear if you have the specific assumptions of the Baer-Meyerson model. CL and type H had a high fixed cost CH. Okay, and if we have this, we can, and that's just our rectangle. Now, of course, depending here, the height of the rectangle is always CH minus CL, and the length is always Q of P. And of course, the quantity depends on the price. And what we have, of course, is PL equals CL. And if you substitute that, okay, if you substitute that, you just take the derivative and substitute it here. If I manage to get it back here. If you substitute it here, okay, in this condition, you just get the result. Of course you can, and that's what you will do actually in the tutorial. You can just set or substitute all these in the welfare function and then derive the optimum. Okay, and what you get here is a very general result. Namely, the price of the high type is distorted upwards. It's distorted upwards unless alpha is equal to 1, that's what you see here, and unless phi is equal to 0, what you also see here. And what is important here, the price is completely independent of the shape of demand. Remember here, there was a Q prime in the previous condition, and it just canceled out because you will, if you take the derivative of delta pi p with respect to p, you also get a Q prime here, okay? And the later result here, that there is no distortion if alpha is 1. So if we don't downweight, in a sense, the profits or the rent of the firm, you just make the so-called, the firm, the so-called residual claimant, give it everything, and you don't care for the rent, and then it will just maximize total surplus. Okay, and this holds quite generally. Hopefully it's clear. I refer to the triangles or rectangles so often. So what we are doing here is actually what I try to show you by the means of this diagram here. Okay, if you start out with a contract which prescribes price equal marginal cost, so PH equals CH, you have to pay this in terms, the red area in terms of a rent to the low type in order to satisfy this or to satisfy the incentive compatibility constraint. Okay, why do you want to do this? Do you want to do this? Yes, actually, because if you don't do that, your consumer surplus in all cases will be this, and this the red rectangle will still be the rent of the low type. If you pay the rent by giving an appropriate transfer to the firm, if it turns out that the term is really low type, you will at least have a price equal to PL equal to CL, and you realize this triangle here in terms of consumer surplus. Okay, that's why it makes sense to implement contracts which lead to revelation of the true type. Okay, that was the first point. Now, so you want that the firm tells the truth, but at the same time you don't want to pay such a high rent. Okay, what can you do? And that's actually our result. That was the problem. The rent is costly. Okay, that's our problem. So what we can do, and that's what we actually derived here in terms of what the optimum is, we increase the price, and that's what I also had. If we increase the price, you will get a different transfer to the high type, because the high type then will make some losses equal to this blue rectangle. And now this reduces. Of course, these are some operating profits here, not operating losses. Okay, might still make losses because the fixed costs are higher, but at least you will reduce the transfer to the high type by this blue rectangle. This reduces the rent of the low type to the green area, to the green rectangle. Okay. Of course, it comes at a cost, because you now distort the price of the high type, and you get this yellow triangle as a deadweight loss. Okay, and so here, what you do then, once you calculate the optimal price, you balance the cost of distorting, which would be the the yellow triangle, with the gain from distorting, which is the lower rent, the red rectangle here. Okay, and here I just did that in formal terms. Downward, this would be just this trapezoid here, this integral, and it applies with probability. So you have this distortion with probability 1 minus phi. So this is just a trapezoid, is just a whole area below the demand curve integrated in say a horizontal problem in a vertical sense, and you subtract here this red. This blue rectangle, and at the same time you get the delta R, and you could even use this approach dWL plus delta R in order to derive the first best here, or the optimum. Okay, I think I make another short break here before we turn to the Lafont-Tirol model. Okay, also here, short break. Okay, as I just already told in the Webex chat, on the one hand, this is of course complicated stuff and you will have to go through it step by step anyway, but we will make sure that you go through it because if you look at the previous exams, we had a Bern-Meyerson problem in all of the 20 previous exams or something like that. So make sure that you really understand it, go through it and prepare it on your own for the tutorial class, and we will have many examples, many different problems. Okay, so we just now move on with the Lafont-Tirol model, which is just another application. Here you see why we chose this general approach, because once we have the general solution, we just can easily apply it to the different kinds of cases, and that's why I'm set it up in just such a nice, elegant way. Okay, yeah, hopefully you're still awake and are able to follow me. It's rather complicated and it always takes longer than I planned, but that doesn't matter. It's really, I think, one of the most important and also very interesting stuff, and hopefully I can convince you of that. Or perhaps I just jump back once here. The point is here, what we have to take into account, and this is a very general point, the regulator will have to pay what is called an information rent to the firm. Okay, and these are these red or green rectangles. We want to reduce the information rent, but we have to pay because it's really worthwhile to pay the information rent, and that's why, or that's what I just explained to you some minutes ago, because we can then realize this further consumer surplus triangle. Okay. That's the information rent. Now, the Lafont-Tirol model, what does that mean? The regulator can observe marginal cost, but not fixed cost. I think I just jump to a diagram on the next page, because that should make it clearer to you. I think we have a nice problem here as well. I just want to show you the diagram, what that means. Okay, I show you the diagram, what that means. So, and the example here is we want to build a new high-speed railway link between Munich and Hamburg. And we know, so if we want to make it a straight line, the costs are very, very high because we need only tunnels and bridges. If we make the longer, and of course, if we make the connection longer, we will have higher operating costs because it just takes longer to drive there from Munich to Hamburg. So if we make the distance longer, we get higher operating cost, higher marginal cost, but we get at the same time lower investment cost. Okay, and the asymmetric information, low investment cost should be clear here, because if you don't have to build so many tunnels and bridges, it just gets cheaper. And the point here is that or the asymmetric information here is that we do not know whether the investment costs, the construction costs, are high or low. Okay, that's what we don't know. And for a given CH, if we have again, we will offer two contracts, and what you will see here, if we have a certain CH, the difference between the high investment cost and the low investment cost will be just the rent which the low investment cost type will have. Okay, that's what we have here, and actually that's what we are going to calculate here. What is the optimal CH? And actually, we really the same thing as we did on the previous slide. So here we now have 3 instruments rather than 2. Again, I was too quick here. We have 3 instruments, namely the price, the marginal cost, and the transfer, because we could also set a price higher than marginal cost. The rent of the type with truthful revelation is just what we all said, operating profit minus marginal cost plus transfer. The incentive compatibility constraint of the low type is very easy, because that was the difference in the 2 lines. Remember, the fixed investment, the fixed cost the high type has given the cost of the high type, and the fixed cost the low type has. Okay, and similar for the high cost type, but that's not relevant. And of course, only relevant is that the participation constraint for the high type is satisfied. Welfare in state I is also the same as previously here. Consumer surplus plus operating profit minus fixed cost minus 1 minus alpha dr, the costliness of the rent. And the point is that the price does not affect incentive constraint. Okay, here for given RH and given RH. RL. So you see no price here, and therefore you don't have an incentive to distort the price. And therefore, you can directly take a derivative with respect to the prices, and you will see price just maximizes the total surplus, and therefore we will get price equal marginal cost. Lafont-Tirol call this property incentive pricing dichotomy. Prices are used to attain allocative efficiency. So if we have a certain marginal cost, the price should be according to marginal cost, and transfers are then used to give the incentives for cost reductions or to reduce the rent. Okay? Yeah, the point is here, again, that the marginal costs are observable. You can observe, the regulator can observe how long this connection between Munich and Hamburg is. Yeah, and here again, our delta pi enters, and it's increasing in CH, okay? So FH minus FL will be decreasing, okay, because it's always a negative thing here, and that's what we already saw in our diagram. I should animate not every line here. That's what we saw here, okay? So if we increase C, the rent will decrease, okay? And again, here you get the delta pi is just this FH, CH minus FL minus of CH, and here you get the minus. That's what we get from the delta pi. And you see a similar optimization problem as in the previous case. Yeah, you now just have not only 2 but 4 variables, but the derivation with respect to the 2 price variables is particularly easy, because that's just meaning you maximize total surplus. So you get PLCL. You will get a chance in a tutorial class to calculate that. And what you get then here is if you take a derivative with respect to CL, okay? You want also to know how long should this connection between Munich and Hamburg be if it turns out that the investment costs FL or investment costs are FL, that is, they are low. And you see CL only shows up here and here. Okay, it shows up only in the profit of the low type, and CL, if you maximize with respect to that, you'll see it's just maximizing minus Q of PL, which is times CL minus FLCL. And this is nothing else than what you have here. This is nothing else than that you want to minimize cost. And you want to minimize cost given some output, and you minimize it by choosing C and knowing that if you increase C, F will decrease. And the first order condition is simply that if you take the derivative with respect to C, you see if you increase C by one euro, I think we already did that previously in the second chapter or so, you get higher cost in terms of Q, but at the same time you save investment cost because it's downward sloping. And what you see here is the result that with respect to CL, you choose the cost minimizing output, excuse me, no, cost minimizing cost here, marginal cost, okay? Whereas the interesting thing is the CH here. That's what you distort, because you see the CH shows up here in the profit of the high type, and it shows up in the rent, okay? That's again in the other state, in a state L, it shows up in the rent of the low type, and that's what we get here in terms of our diagram. By changing CH, by increasing CH, we can reduce our L. That's what you see here. This is now what means delta pi is increasing, that is the rent is decreasing if we increase CH. And as you now see, you not only get this cost minimization plus you also get this effect from the reduction of the rent, and that will lead to the case that this is positive. Okay, the low type, so it's higher. You do not any longer. You have a higher CH, and that means you do not any longer produce cost minimizing if you are in a high state. Okay, so and therefore high cost produces at too higher marginal cost. Of course, always unless alpha is equal to 1, as we are then not considering the rent. Okay, again, this only will become clear once you look into the details into the assignment we have here. Okay. Okay, now actually we were in a wonderful world. First of all, we looked into the case in which even though we have asymmetric information, we can implement the full information outcome because asymmetric information is not socially costly. Because the standard kind of contract is incentive compatible. Then we looked into the Baer-Meyerson and Lafont-Tirol model, where unfortunately full information contracts don't work. But if we observe the incentive compatibility constraint, we really can reduce the rent of the firm and nevertheless get the gains from the revelation of the type. Okay. Now we turn into the case in which the asymmetric information is really social costly in the sense that we cannot, or where it's not sensible, there it doesn't make sense to induce truthful revelation, or it's not even possible. Okay. The point is here we get then a pooling equilibrium. The point is if the full information prices are ordered in the wrong way, if the low type price is higher than the high type, then private and social incentives are opposed, and it's too costly to obtain firms' private information. And we just look into the first case, and the second case will be, well, I don't even remember what the second case, I don't know whether we have a second case. Okay, we will see. Actually, we will have a second case, but only in the commitment part, and we won't go into detail there. I make a short break here, and because it was sufficiently complicated, and just ask for a question briefly. The first case and the second case will be, well, I don't even remember what the second case, I don't know whether we have a second case. Okay, we will see. One example, unknown consumer demand, now concave cost function. That is, marginal costs are decreasing, and that's again what you will see in a second. If marginal costs are decreasing, low demand will have a high price and high demand will have a low price, even though incentive compatibility requires just the opposite. And therefore you will see the optimum involves pooling. You charge the same price irrespective of what the state is, whether it's a high state or a low state. You get similar problems in commitment, but you will see that later on, probably not today. Now, pooling, what does this mean? Suppose we have decreasing marginal costs, and I think just go through until we get our diagram here. Okay, so again, low demand and high demand. Okay, but now downward sloping marginal cost curves. These are not completely irrelevant in terms of say, the network industries we have. Typically, we don't have downward sloping marginal costs, but downward sloping average costs. But if you have, for instance, if you buy some services from such a network industries which have some kind of break-even constraint, your price schedule might even look like this here. Okay, and what you immediately see here, so these are the concave and decreasing concave cost function, which lead to decreasing marginal cost. You see that pi L is greater than pi H. Okay, even though high demand is higher than P, and the probability, this would have been PL in this case, not pi L. Of low demand is again phi, and that's just taken from the previous example with the increasing marginal cost, where we just set the first best prices, price equal marginal cost. So PL would be the price for the low type, and PH would be the price for the high type, and the transfer was simply equal to the minus the profit, and that means it would be F, the fixed cost, minus any operating profit arising. And what I want to show you now is that such a situation is not implementable here. Okay, Now, first of all, what would be my note tell me to draw the full information outcome and the respective transfers here. The point here is in terms, if you have full information and you have a low type, the low type would just set this price. And here you see a very small triangle. Okay, this very small triangle. Costs, variable costs would be above the revenue. The revenue just simply being this rectangle here. Okay, and you would get then a small transfer above the fixed cost. Okay. Now, what happens if a high type, or actually would have a high type, have an incentive to claim to be a low type? Now, the high type, given this price, would serve or would sell these units. Okay. So you see, it would make this in terms of operating profit, and it gets this in terms of a transfer plus the fixed cost, and of course this would really be the gain from claiming L if you're high. Okay, you have an incentive to deviate from the first best contracts. Now the next point is, what would be in a situation if we look into the high type? Would or if the high situation, would the low type have an incentive to deviate from this here? Now, if you know you're a high type, the contract would say, okay, this is your revenue with the high type, and your cost is just all the area below the marginal cost curve. So what you would get is just a transfer this high minus plus a fixed cost. Okay. Now, here with the low type, if you claim to be a high type, given this price, you only sell this amount. Your loss is only this here, but you get a transfer equal to the full triangle. So usually the purple triangle is your gain from claiming H if you're L. So what is the result? Both, given the full information outcome, both types have an incentive to deviate. Both incentive compatibility constraints do not hold. And can you improve the situation? If you want to make the incentive compatibility to hold for the high type, it gets worse for the low type and vice versa. So it is not possible to implement that. Okay, and that's about it. Okay. So in the notes I wrote in detail in formal terms, so it's not the case, but it should hold here. What you see, it's just not implementable. You get the wrong kind of deviation. Both high and low type have an incentive to misrepresent its type, and both ICCs cannot be satisfied at the same time. Okay. Yeah, actually, it was the only example I gave you. Thankfully, it's not so many situations where we cannot implement that. But nevertheless, you will see in next part, when we discuss commitment, it might also be similar, that you just don't want to know what the type is, and you choose pooling equilibrium not voluntarily. Okay. Now, actually, so I'm done with this rather heavy topic on regulation under adverse selection. The next part will be just 2 or 3 further topics or refinements where we start with audits. So until now, our regulator was not very well informed. The regulator only knew that it's high or low type and only knew the probability distribution, not more. I think I have another 2 minutes, but that won't be sufficient. Okay. I think given that it was such a demanding topic anyway, I stop here. What you will see in this part is rather interesting. Actually, do you trust in what you could put it differently? If you're a regulator, you might just tell an auditor to go to the company and find out whether its costs are high or low. Okay, and the point is, will you believe that if it tells you this firm is a high cost firm? Is that true? Maybe it's not true. Okay, we have some experience, in particular, for instance, with rating agency. They come under huge attack in terms of the financial crisis because they told investors that the subprime loan bonds are somehow good bonds. Okay, and it turned out that they were rather bad ones, more like junk bonds. And so you see, a signal is not always reliable. The point is here, what you will see and what we will show you next time is, even though it's not perfect, this signal, it helps you if it's informative. So if it tells you it's a low type, it's more likely that it's a low type than it's a high type. Okay, and If you have this, and if you have risk neutrality, you will see you can implement also the full information outcome. But for that, you will have to wait, well, not another week, but only until Thursday. I leave it at this here, and thank you for your participation. And I'm available for further discussion in Webex right now. Hopefully you could digest what we did. It should become clearer once we do it in the tutorial class. And as always, I'm available for some questions and discussions in Webex right now. Thank you. Okay, so we are done. Actually, rather interesting. Probably the City Council of Gießen should have listened to my YouTube lecture here. Have you ever heard of the Greensill Bank? Actually, the City Council of Gießen wanted to avoid negative interest rates on their accounts, and they invested, I think, 10 million or so in a strange bank called Greensill, and they listened to a rating agency, and this rating agency told them, oh, it's a good investment. Actually, it turned out that these 10 millions are lost right now. Okay, same schedule as last year, and I think I could show you just the assignment for next week. So we needed to have this lecture today because you will see that we have the Baer-Meyerson question in assignment 8. So we will, so that you have sufficient time to prepare that, we will do that or do another lecture on Thursday, so you have time to prepare assignment 8 rather thoroughly. Okay, yeah, thanks again. I'm available in Webex for some more questions, and I wish you a nice day and see you on Thursday. Bye.